Yes, sir.
Okay, please run it and show me again. Explain me which one, what is the triangular one? Please explain me.
Yes, sir. Like first OPM's waveform is this one's the red one. That is the square wave. And second wave's waveform is like a triangular wave. And output of this comparator is this one, sir. Blue one. Comparator's waveform is this one, the blue one.
अच्छा. This is for isolated
No, sir. This one is for non-isolated, sir.
or isolated one.
Sir, this one is for non-iso. Sorry, sir. This one is for isolated, sir.
अच्छा.
This is one is the waveform, sir.
अच्छा, can you see one thing? Can you show me one thing?
Yes.
Go to your simulation. Can you put on oscilloscope? The before this is isolated. Am I right?
Yes, sir. Isolated, sir.
So can you please show me the response? Just input of that opto-isolator and output of the opto-isolator. Additional scope, can you please incorporate? Then show me the results.
Sir, again, sir, repeat, sir. What to do, sir?
Take an oscilloscope, okay, and
Yes, sir.
in the same oscilloscope we need to see that input of the opto-isolator and output of the opto-isolator.
Sir, I don't know, sir, how to do, sir.
ना ना, ऑप्टो आइसोलेटर का इनपुट एंड आउटपुट दोनों को दिखना है इन ऑसिलोस्कोप में. एक ऑसिलोस्कोप वहां इनकॉर्पोरेट करो, इंक्लूड करो. फिर दो चैनल होता है ना ऑसिलोस्कोप का, एक तुम डालो ऑप्टो आइसोलेटर का इनपुट टर्मिनल में, अनदर वन इज ऑप्टो आइसोलेटर आउटपुट टर्मिनल में. देखना है बोथ आर इन फेज. व्हाट इज द डिफरेंस बिटवीन टू सिग्नल, दैट आई नीड टू सी.
Yes, sir.
सिंपल चीज, दिस इज वेरी सिंपल. सिग्नल को दिखना है. We need to see the signal, nothing else.
one is visible, sir.
Can you please zoom it?
Unable to do, sir.
Okay, leave it. Okay,
Okay.
okay. So next, uh, roll number 296.
Yes, sir. Sir, I'm not able to use multisim now. I was doing that evaluation thing, but it got over.
I'm not getting what happened.
Sir, sir, I'm not able to use multisim now.
Okay, so whatever you are doing, I don't know, but when we are, you know
Sir,
that
I'll
from
share
next
my
week.
screen and show you.
No, you show me if you have the results. Only you can show me. Okay.
Sir, my multisim is not working now.
Achha. Okay,
Sir,
next one is roll number 298. Absent. Okay. Roll number 413.
Yes, sir.
Absent.
So, showing, sir.
Ah,
Yes, sir. This is non-isolated gate driver circuit. Hello, sir.
huh. Please run it.
Yeah, this is the output of first op amp.
Okay.
This is the second op amp output.
Okay. Good. This is for non-isolated. Am I
Yes,
right?
sir. Yes.
Okay. Now show me isolated one.
So this is output of first op amp. Square wave output, which is like a stable multivibrator.
Okay. Both are in phase. Did you see that output of the multivibrator and output of the MCT2E both are in phase or both are in different phase?
No, sir. I didn't see.
Okay. So both are in.
चलो सर
ওকে ঠিক আছে ওকে ওকে ঠিক আছে থ্যাংক ইউ নেক্সট ওয়ান ইজ 284
Yes, sir.
হ্যাঁ show me your simulation
Sir, is it visible?
yes it is visible
So this one is for the non-isolated.
acha aditya can you please tell me what is the purpose of this R4
Sorry, sir.
what is the purpose of this R4 registers aditya
Yes, sir.
do you perform the simulation by yourself or you
Yes.
take help from your friends?
No, sir. Myself, sir.
Okay, so now tell me what is the purpose of this R4?
No, sir.
Bolo. If we change the value of R4, then what happened?
So R4.
Yes, R4.
Sir, it will increase.
Huh?
Sir, it will increase.
Which one is increase?
The pulse wide will be increased.
Pulse?
What?
Pulse width?
Yes, sir.
Are you sure?
Yes, sir.
Why? Why can you please tell me?
No, sir.
Huh?
No, sir.
Can yes sir, no sir, what you are telling?
I can't describe, sir.
Okay, now show me the simulation results for isolated.
These are isolated one. But sir, I am facing some issues with the simulation, sir.
Acha, what issues you have faced?
So nothing is coming actually, sir. Hello.
Tell me.
Hello, sir.
Am I audible?
Yes, sir. Yes, sir. Sir,
Tell me.
but the like simulation is not coming anything like when I am doing this simulation. So this is the for the isolation portion. But when I am doing the simulation, there is nothing, sir. It's not coming anything, sir.
Some error is there, that's why it is not coming.
Yes, sir, but like as
Make
per
it
the
auto. Make it auto still. Is it running?
sorry, sir.
First, run first. Run your simulation. What is the difference between isolated and non-isolated? Only after isolated need to include. So for that, it's not coming. Why? It should come. Do you run the simulation?
Yes, sir.
Minimize karo. Graph minimize. No, it is not running. No. Press the
Yes, sir.
green
Yes, sir.
button. Green one. Press it.
Yes, sir. This one, sir.
Press it. You made some mistake. I think you are giving biasing voltage polarity problem is there. I think so. Maybe some biasing voltage polarity problem is there. Class VCC, maybe you are connected with minus voltage. Maybe you need to check it.
Okay, sir.
So next one. Next, who want to show me the simulation? Roll number 292.
Hello. Yes. Sir, is my screen visible?
Yes, it is visible.
This one is for non-isolated and this is for isolated one.
Sure.
For isolated, I'm getting this as output, and this is output from the first op amp, and this one is from the second op amp, and this one is from the third op amp.
Okay. Response.
Hello?
Tell me, if we vary the R4, then what happens?
The frequency will change if we'll vary the output.
Okay, did you cross check it?
I have to prepare the table. Like we have not prepared. I've not prepared the table for this. Only I have done one simulation.
Acha.
And this one is for non-isolated. This one from the first op amp, and this value is from the second one, and this is from the third one.
Okay.
Should I share the report as well?
If you have the report, please share it.
I have not prepared the table.
Acha.
Only the like I've tried for balancing. Is the screen visible, sir?
Yes, it is visible. Theory portion, again, that right alignment, make it justified.
Okay, sir.
Left alignment, make it justified.
Sir, this is
Okay. Observation table is required.
yes, sir. I will make it after that.
Okay. Okay, ठीक है, good. Okay, now I'm sharing my computer screen. Is my computer screen is visible? Hello.
Yes, sir.
So
Yes,
our,
sir.
our next simulation is simulation of basic DC-DC converter. Okay. So what are that basic DC-DC converter? You know that buck converter, boost converter, buck boost converter, like that. Half bridge as well as full bridge converter. Okay. These all are the very basic DC-DC converter and applications. Okay. Suppose you know that buck converter means we're making that output voltage, buck converter output voltage is less than your input voltage. Boost converter, it is known as step up converter, means whatever input voltage you are giving, so more input output voltage you are getting, but without changing the power. Power is all the cases constant. Power constant means what happened? Your current amplitude may be changes. Okay, so voltage may be different, but current is voltage may be increased, current will be reduced. The power, more in simple way, power make it constant. Okay, so you know that what are the basic structure of the buck converter. Here you can see the diagram. So one voltage source is there, then you connect one switch SW. Okay, switch is there, then inductor, and so inductor and capacitors are there. That inductor and capacitor is working like a filter, and here you can see the load resistance, and one diode is connected here. Okay, in between switching terminal and that negative terminal of the voltage source. So when switch is turned on, okay, then what happened? When switch is turned on, then inductor power is passing from flowing from input side to output side, means source side to load side, through that inductor, capacitor part and load resistance. When switch is turned off, then what happened? So voltage source will not be in the circuit. So in that's the way backside you can see the current will be flowing through the diode. LC filter is there, through the diode it is flowing like that. Okay. Here we can see the basic calculations of that buck converter. So how to find out the average one. Okay, so very simple calculations. Okay, so here one simple question may come as using the switch. Okay, and we are talking about that frequency. Okay, so basic question is that so inductor and capacitor both we are using. Okay, question is that as it's a DC circuit, okay, how the frequency is related to here. Okay, one basic simple question is coming. The answer is that it's all the cases which is working in high frequency operations. Okay, suppose the switching frequency is more than 20 kilohertz. Why more than 20 kilohertz? So up to 20 kilohertz, what happened? Where there is a noise. Okay, so as 20 kilohertz is audible range, that's why we are facing the noise. Okay, so that's why it is more than 20 kilohertz. Okay, that's why it is more than 20 kilohertz. Okay, I hope you are getting that point. Okay. And for that high frequency, so there is no chance to it's a DC, so highly oscillating. Okay, highly oscillating, automatically it is oscillating, and it's a high frequency operation, you can see. Okay, then in case of boost converter, you can see the structure of the boost converter. Current is increasing, then decreasing. It's your what is your inductor voltage. Okay, at turn on condition, you can see when switch is turned on. Okay, so total voltage V in will be coming across your inductor. When switch is turned off, which voltage will appear across your L? So output voltage, input voltage minus output voltage. So your output voltage is higher than your input voltage. That's why negative voltages appear across your inductor for turn off conditions. And current is charging, then discharging, again discharging, like that it will happen for the converter. Okay. Now you can do the simulation for buck converter. Okay, so we are using some switch. Mode diode is there. Values are given here. Okay, directly we are incorporating the pulse. Okay, that pulse is there. Okay, and directly we are getting the response of buck converter in open loop. These all are doing in the open loop. So all the values are given over here. Okay, and we can see the waveforms of the gate pulse. Our main target is that to find out the dynamic response. Okay, so transient response we need to see how is it look like. Okay, so here we can see the transient response. Okay, so here we can see the transient response. Initially it's look like a under damped type of system. Okay, oscillatory, then it is fixing up. Okay, so it is under damped type of response. Okay, I hope you are able to see the nature of the response. Okay, then we do that the same thing. It is for voltage. This is current. Okay, and we are using the resistive load. Okay, that's why they are in more or less in phase. So you can also use that different type of load for R load. Then you can use it for RL load. Okay, and RLE load. How it will look like it. Okay, and you can prepare an observation table. Here only R load is given. The pending thing means RL load and RLE load. How is it will look like, so that you can do it in your simulation and report. Okay. Then we can calculate that how much duty is there. Okay, based on our response. After that, we are doing the boost converter simulation. In boost converter simulation, what we are doing, we are considering the impurities like parasitic elements. So in ideal inductor do not have any equivalent series resistance, ESR value. Okay, an ideal capacitor also don't have such type of thing, equivalent series capacitance. Okay, so what we are doing, so we are including resistance and both the cases, resistance in inductor, resistance in capacitor. Okay, both we are incorporating over there. Okay, and we can see the response of that boost converter. Okay, so here the boost converter response is there. Okay, when first structure is there, then we can plot it. Okay, how is it will look like? The parameters values are given, then it is gate pulse. Okay, then boost. So why this is that oscillator? You can see the triangular one, basically charging, discharging like that. Okay, that's why it is it is a steady state, transient and steady state. Both we need to see. Okay, initially some undershooting is there. Because of that, there is a problem of non-minimum phase in boost converter. Okay, then you can calculate that duty cycle, and this is for what? This is for half bridge, asymmetrical half bridge. Okay, asymmetrical bridge you can also say. Okay, so asymmetrical bridge to switch is there, control switch. Okay, and their responses, how it will be look like that current voltage wave from gate pulse. This is gate pulse. Then dynamic response means voltage wave from. Okay, how it will be look like that. Voltage is varying from plus 100 to minus 100. Okay, and current is always in positive direction. So okay, triangular one. Now we can go for that full bridge converter. So both the control switch is there. Okay, and RL load we are using. Now it is the waveform the gate pulse for the both the sequence. Okay, and current. So current also varying positive as well as negative. Okay, so asymmetrical bridge, what we have observed, current is varying only positive cycle, positive half. But here voltage is varying plus 100 to minus 100. But here for this bridge, current also varying from positive to negative side. Okay. So these are the very simple calculations, very simple experiment. Okay, simulations. Okay, I'm sharing this content to you. All of you able to understand? Is there any confusion?
No, sir.
Do you get that file? I have shared it through the chat box. Do you receive it?
Yes, sir.
Because am I audible?
Yes, sir. Yes, sir.
So now the MCQ test will be there. After that, the Viva will be there. Okay. So please share that exam link. Then for the Viva, you will get a call through MS Team. Okay. So after completion of this MCQ test, you can leave the meeting. After that, you will get a call for the Viva. Okay. Individual call through MS Team. Okay.